I was going to say good evening, but I don't know when you're watching this. Okay. Let's do a couple more problems from 7.4. And so I'm lifting these right out of the textbook. Let's see what we've got here. Whoa. It's a whiteboard catastrophe there. Plus 1 over m equals 1. Solve for c. So let's write this up here. Okay, solve for c. So we want to get c by itself. Again, we're in a zone here where there's no new skills really being introduced. No new skills. But it's using the skills you have. I mean, I could, what would be an analogy? I don't know, cooking a new type of food. You already know how to cook, and you have all these ingredients, but you're putting together in a different way. Solve for c. Well, we want to get c by itself, so let's get rid of this 1 over m business. Let's get it over on that side, so we'll subtract it. And this is not the only way to do it. There isn't a only way to do most of these problems, but maybe this is the most obvious thing to do. We could proceed in a couple of different ways here, but again, when I see two things that could be added or subtracted, I usually get an overwhelming urge to add or subtract those things. So let me go ahead and do that, the routine regular way for fractions, right? So m minus 1 over m, and then I'll take the reciprocal of both sides. I'll use that shortcut that I talked about in the last video, and I feel like it's a somewhat dangerous shortcut maybe, but it's pretty handy. Remember, when you have one and only one rational expression on each side, you can flip both sides over. If you have more than that, you can't. You get a false answer. Okay, let's try another example. Again, this is from 7.4 in the textbook. Let's just try, maybe those are all sort of similar. Let's see if I can find something different here. Now, that's about it for 7.4 as far as the types, but you need to practice those. Let me go to 7.5 here. It looks kind of the same. Well, word problems. So let's see. I'm going to go ahead and read this one. I should probably tell you which one this is. So this is 7.44. Example 7.44. Example. So you can take a look at it and you can read it. I'll read it out loud. When pediatricians prescribe acetaminophen to children, they prescribe. Wow, there's several different ways in which you can do this, so I don't even know which way they're going to go at right now. There's a very, very famous formula that involves logarithms and exponents, but we haven't gotten to that yet, so I don't think we'll be using that one. They prescribe 5 milliliters of acetaminophen, 5 milliliters for every 25 pounds of the child's weight. Now, when I do a word problem sometimes and I don't know where it's going, maybe I'll just stop and dwell upon or meditate. 5 milliliters for every 25. Okay, it makes sense. 25-pound child, 5 milliliters. It was a 50-pound child. Well, it'll be double that, right? So if Zoe weighs 80 pounds, how many milliliters of acetaminophen will her doctor prescribe? There's no doubt about it. Word problems just take practice. What just occurred to me is how to solve this. And then the question you should have is, how did that occur to me? And if I get really deep enough and introspective enough, I don't know. I guess I could just say it's practice, practice, practice in doing problems until you get the hang of doing them. So for every 25 pounds, so I'm going to let x be the number of pounds, and I'm going to divide it by 25. And the reason is this. I'm thinking, look, you have a 25-pound child, this quantity here would give me 1. If I had a 50-pound child, this quantity would give me 2. And in a way, the 1, the 2, or 75-pound child, this would give me 3. That's the number of doses that I'm going to give. So I'm going to take this and then multiply by the quantity in a dose, which, as I refer back to the problem here, is 5 mLs. So we'll multiply this by 5, and this would give me, for right now, let me just say this is, say, I don't know, what letter do I want to use? I was going to use D for dose, but I just referred to 5 as a dose, and we don't want to give 2 doses or 3 doses. I could use quantity seems kind of a natural thing to do, but Q, that could look like a that could look like a zero. Um, I guess I'll just use capital A for amount. This is the amount that we're going to give you. Also, maybe the A goes along with the acetaminophen, but you can use whatever letters you want. I also could say f of x, where the quantity is a function of x. But for right now, I'll just go ahead and write it like this. Oh, and what was the question asked? I almost forgot. If Zoe weighs 80 pounds, how many milliliters should we give? Well, we just put an 80 in there and calculate it out. There's no algebra. At this point, there's no algebra being done here. We'll just put an 80 divided by 25 times 5, and that'll give us the amount. Let's see if we can do a little bit of canceling here. 5 goes to 80. How many times? 16. So we'll give 16 milliliters. Oh yeah, one thing you should do, check to make sure your answer seems to make sense. 25-pound child, 5 milliliters. It's by volume, milligrams, mass. 50, is this pounds? Oh yeah, it's always weird when we're using both. We're using English units, American Standard units, and metric units. But this kind of thing is done in medicine sometimes. Hopefully less and less. I used to teach for a nursing program, and so I was really up to date on these things. But it's been a few years since I've checked in with what's going on in the world of medicine. 50-pound child, 10. A 15-pound child? Wait, not a 15-pound child, sorry. 25-pound child, 5 milligrams. 50-pound child, 10 milliliters. A 75-pound child would be 3 times 5 or 15, and this is a little more. So, in other words, it's a reasonable answer. Sorry, that was not a very interesting question. Well, I haven't really done very many problems this is the first time I've done problems for the book here in class. Let me try, oh, wow, everybody's favorite. As soon as you start talking about geometry, people start losing their minds. Maybe rightfully so, maybe not. Depends on what sort of geometry you're doing. But let me go ahead and do example 7.45. So example 7.45 from the textbook. And they're giving us a preface here, if hopefully you're reading the book, and they start talking about similar triangles. I'm sure that's something you've heard of, but if not, I'll discuss it when I use it in a minute here. And there's a diagram here, and it says, and I'll draw the diagram, but it says, again, example 7.45, so you can look at the very nicely drawn diagram in the book. On a map, San Francisco, Las Vegas, and Los Angeles form a triangle. I was going to say any 3 points on a plane form a triangle, and they do, so there's nothing startling there. The Earth is actually not flat, despite what you may hear on the internet. But we're going to pretend it's flat for this problem, at least I'm pretty sure, because if we do this problem on a sphere, well, the whole thing could get more difficult. So we're just going to pretend it's a flat Earth right now. So San Francisco, Las Vegas, and Los Angeles. So San Francisco and Los Angeles down here, LA, and Las Vegas over here. I actually don't know the latitude. See, oh yeah, the latitude of Las Vegas I think it's north of Los Angeles, but I forget the exact numbers. I think we're here at 32 degrees north latitude right now. Let's see, the figure on the left below represents the triangle formed by the cities on the map. If the actual distance from Los Angeles to Las Vegas is 270, so Los Angeles to Las Vegas is 270, more or less, I suppose. Hold on a second. If the actual... Oh, I was trying to answer the question before I read the whole question. So I should probably read the whole question. I'm wondering if there's a typo here. The distance between the city is measured in inches. The figure on... Oh, I got it. That's why there's two triangles. So first I have a triangle that looks like this. I won't even try to duplicate these similar triangles, but we have a picture. Here's Los Angeles, Las Vegas, San Francisco, and the diagram on the left has 1, 2.1, and 1.3. And the idea is if these are similar triangles, the ratio of corresponding sides are the same. Now, you've probably heard this before. What does it mean? This seems to be an obvious thing, or at least it's intuitively plausible, and it is true. What we're saying is if you took this side divided by this side, here, let me draw this triangle over here. Hey, reasonably similar. If we took this side divided by this side, it would equal this side divided by this side. Or if I took this side divided by this side, it would equal this side divided by this side. Now I notice in the textbook, if you look just above this example, they state this. It's printed out and they state what we mean by using similar triangles. Or maybe they state, I could scroll up here. They might state this is a theorem. They say property, so they're not proving it. And you don't need to worry about proving this or whether it even can be proved or it's just an axiom. But at any rate, at that point, where they want us to find the distance from Los Angeles to San Francisco. So from here to here, let's call that x. And so the idea is, well, for example, there's a couple of ways you could do it, but I could take 1.3 divided by 1. This divided by this is equal to this divided by this. So x divided by 270. And then divided by 1. I mean, look, then you just do the math, and the math here is pretty easy, but what we get is x is equal to 270 times 1.3. Hey, this would be an ideal time maybe to use a calculator, but let me show you something. Sometimes you get lucky, or maybe not. Hold on a second. We'll check this out. X is equal to 270. Now, what is 1.3? It's 1 3/10. 1 3/10. So it's 13/10. Notice I get some nice cancellation here. Now, it's not the end of the world. 27 times 13 would be 270, and then 81, so 351. But definitely double check, my arithmetic on that. So 351, which sounds roughly right. Yeah, it's roughly 500 miles from here to San Francisco from San Diego, and here to LA is a little more than 100. So whatever. I mean, at least it's in the ballpark. It's not crazy. Hey, let's do this a different way, just to make sure that this works. Well, hopefully I remember my answer there, 351. Because what I said is I could have done this. I could have done x divided by 1.3. This divided by this is equal to, for example, this divided by this. 270 divided by 1. And so x would be 270 times 1.3, which is what I did just a minute ago. So it is the same answer. Okay, so the algebra here is not too tough. Let me just scroll down this page before I end this video and see if I see any other real, let's see if I see any challenging problems. Hey, make sure you practice these problems, and if you have questions, let me know. Some of you have been, emailing me questions. Some of you haven't heard from yet, but, if you got it, you got it. That's okay. Uniform motion problems. We talked about those. We did 2 equations and 2 unknowns. I got a problem. It's very classic, and it's a uniform motion problem, and this is uber classic. And I tell you what, this is a good one to ask somebody that you know that you want to torment. Once I'm going to show you a way to do it that's going to make it seem almost cheating. It's going to make it seem almost unfairly easy, but at first it won't sound easy. And again, this is a very classic sort of problem. And I could start off by saying you have a boat in a river or an airplane in a current of wind. That part of it doesn't really matter. But let's say you had a boat and it had a motor such that in still water it always ran at the same speed. So you put the boat in a calm lake and it always goes at the same speed. But instead what you do is you put it in a river. So here's the river, and I'm trying to indicate that the water's flowing this way. And it's an idealized river because rivers don't actually flow this way, but I don't mean up and down. I mean, I want the velocity at any point in the river to be the same. So, a lot of assumptions here, but otherwise the problem would get outrageously difficult. And suppose that you are told suppose that you are told that going upstream, you're able to travel 7 miles in, let's say, 5 hours. And then you turn the boat around and you come back downstream, let's say 11 miles in 2 hours. Okay. So you're able to go upstream 7 miles and it takes 5 hours, and you come down 11 miles in 2 hours. The question is obvious, and the question is, you should be thinking right now what the question is. What is the speed of the boat in calm water, and what is the velocity of the water, the speed of the river? And this problem right here, it just seems very challenging if you've never done it before. And I've seen people solve it in some very, very complicated ways, but if you don't mind, I'm going to try to solve this in a very simple way. I mean, it's kind of a catch to everything, because everything I write down, you could ask, how did I think to do that? Well, this isn't the first time I'm doing this problem, so I'm not even sure I'm really thinking about anything right now. But the first time I did this, or in recent memory, whenever I have a uniform motion problem involving distance, uniform motion just means the velocities are constant. Now, they're really not constant here. We have one velocity going up and one velocity going down, but the velocity of the boat and the river taken separately are constant. Well, what do I think of? I think of velocity is equal to distance divided by time. Remember, that's the definition of velocity. Driving in your car, miles per hour. Miles per hour. You wouldn't say hours per mile or miles per hour. So this is something that's known to you. There's no way you can forget this. However, if I multiply both sides by t, I get this equation here, which is probably a little bit easier to think about or to work with. Now, let me think about the trip going up against the river. How far does the boat travel? 7 miles. What's the velocity? Well, this is the part that requires some, I don't want to say like ingenuity or cleverness, but I don't know. I'm going to write something down right now. And, you have to think about this. I don't know what else I can really say. What's your velocity when you're going against the current? Because it could be air or water. It's the velocity of the boat minus the velocity of the river. For some reason, I'm thinking with those walkways in an airport, and you could walk with them, or they move, the people movers, or whatever they're called, moving walkways. You can walk with it, or you can walk against it. At times, how long did that take? 5. And what's the distance coming downstream? 11. And the velocity here is the velocity of the boat plus the velocity of the river. And that took 2 hours. It's 2 equations and 2 unknowns, nothing to it. I'll go ahead and solve it right now, but that's a piece of cake. I mean, if you want, you can even throw this in a 2 equation, 2 unknown solver. No big deal. What is a big deal so far, I don't think AI is there yet that you could scan the words of this problem and it would solve it. I don't think. New things are being developed all the time, so I don't actually know. But at this point, you say, you're triumphant, you're victorious, it's solved. You say, just give me a minute, I'm going to do the regular 2 equations and 2 unknowns. So let me go ahead and do that, just to finish this off. We could do a couple of different ways, but let me go ahead and do the distributive rule here. 7 equals 5 v sub b minus 5 v sub r. And let's solve it for 5 v sub b. I'll add that to both sides, 7 plus 5 v sub r. We'll divide both sides by 5. So there's the velocity of the boat as a function of the velocity of the river. And we'll take this here, and we'll go ahead and substitute it in there. Give me some room here. I don't need this anymore. So we get 11 equals, 7/5 plus v sub r plus v sub r times 2. Let's go ahead and add like terms, 7/5 plus 2 v sub r times 2. Do the good old, now this is all the routine stuff, right? Nothing new here. Good old distributive rule. 14/5 plus 4 v sub r. I don't need the parentheses there anymore. They didn't hurt anything, but let's subtract 14/5 from both sides. So what does that give you? 41/5 4 v sub r. And did I do the math right? Hey, you should be double checking it. Is 11 minus 14/5? 55 minus 14. Yeah, okay. So divide both sides by 4, and you get the velocity of the river is equal to 41 over 20. And I guess my units would be miles per hour because I used miles and I used hours. And then come back here. I don't have I can't see what I'm doing here right now. So let me make sure that this is visible. Let me erase this. Oh, there's the velocity of the river. There's the velocity of the boat. Let me have a little bit of room here. And then I'm going to decide if I want to show you something which, again, it'll seem unfair or make these problems really, I don't know, too easy in a way. But what the heck, why not? So the velocity of the boat is equal to 7/5 plus the velocity of the river is 41 over 20. And we just have to add these two up. So what do you get? 69 over 20. Again, you might want to double check that. I feel like my brain was barely focused on that. What's 28 plus 41? Yeah, okay. So there's the velocity of the boat and the velocity of the river. Fine. Now, here's what I'm a little reluctant, but why not? It's true. Let's go back and see if we can get a template for this, because remember we had a template for mixture problems, and now we can actually get a template for this particular kind of problem. Now watch out, it's only going to work for this kind of problem, not for every problem under the sun. What did I have here? This was the time to go upstream or against the current, and that equals the velocity of the boat, or it could be an aircraft, or whatever the craft is. You know what? Let me put C for craft, because a lot of times you see this as an airplane. Minus the velocity. Oh, geez, I was going to use C for current. V for vehicle? I don't know. Hey, you know what? Boat, river. I'll leave it like that. And then what was this right here? This was the time. Wait a minute. This was the distance that we went upstream. And this is the time to go upstream. And then we had the distance to go downstream, or the distance that we traveled downstream. And the velocity of the boat plus the velocity of the river times the time it took to go downstream. Now, this is a template that'll work. And notice there are 6 quantities, 2 distances, 2 times, and 2 velocities. The problem has to give you 4 out of the 6 of those quantities. If it gives you 4 out of those 6, you plug them in that template, 2 equations and 2 unknowns, you're as good as done. Okay, so 7.4. Next video, 7.6. I'm thinking that maybe we'll skip that. I'm not. Well, it's actually pretty good stuff. Now, so next video we're going to do 7.6, and then we'll move on ahead into chapter 8. So that almost finishes chapter 7, except for 7.6, which I reserve the right. I'll let you know next video. I may put 7.6 on hold. Okay. Until the next video. I got to find the off button here. Okay.